Good afternoon, everyone, and I'm Cherry May Cruz. I'm going to report the unsteady flow calculations. But first, what is unsteady flow? Unsteady flow is a flow that occurs while the pressures or rate changes with time. So, the unsteady flow is defined as the fluid flowing condition at which the rate of change of pressure with respect to time at any position in the reservoir is not zero or constant. So first is the diffusivity equation. Diffusivity equation is one of the most important equations in petroleum engineering. The equation is particularly used in analysis while testing data where the time is commonly recorded in hours. The equation can be written as partial derivative squared times P over partial derivative R squared plus 1 over R times partial derivative of P over partial derivative of R equals to fraction of viscosity times Ct over 0.000264 K times partial derivative of P over partial derivative of T, where K is permeability or MD, R equals to radial position, P is pressure, Ct is total compressibility, T is time, and porosity or fraction, then U is viscosity. So, diffusivity constant. The term 0.000264 K over fractional of viscosity times Ct is called the diffusivity constant and is denoted by the symbol of N or nu equals to 0.000264 K over fractional of viscosity Ct. The diffusivity equation can be written in a more convenient form as partial derivative of squared times P over partial derivative of R squared plus 1 over R times partial derivative of P over partial derivative of R equals to 1 over N times partial derivative of P over partial derivative of T.
Radial flow, ridiculously more complicating part of this topic and your life. Well, this took me hours to draw. Does it look scary? No, it doesn't. It looks like a piece of cake to me. The difference between radial and linear is simple. Linear we use the term x for distance, but in radial we use r, which represents radius. Again, we are finding the equation of mass conservation, but this time in radial flow. So this is the formula for mass in, where flow rate is substituted with area times velocity, and area is further expanded using the area formula of radial flow. Steps are repeated for mass out too. The volume of control volume is differentiated in terms of radius, and then delta R is moved to the right and substituted in the mass accumulation formula. The final equation of mass conservation is derived as following: mass in minus mass out is equals to mass accumulation. The whole equation will be divided by 2 pi r h dr. Now it looks shorter but still complicating. To further simplify this equation, we take delta r and delta t as our limit, and yes, we've got a shorter and simpler equation which we call it as continuity equation. Famous guy who drove us earlier has came back to life. Moving area to the left and substituting it with V gives you transport equation. This equation is substituted in our continuity equation. The equation on the right is differentiated using the product rule. I've explained clearly on how to perform product rule, and if you're still having problem, call me maybe. Taking rock compressibility into account, The formula of Cf is substituted in the equation when the chain rule is applied on delta phi over delta t. Can you realize that the steps are the same as linear flow? We assume that we have homogeneous reservoir as I mentioned earlier. We will have a constant viscosity and constant permeability, so throw away both unknowns which are constant out and differentiate what's in using product rule. Next, we differentiate density in terms of radius and time by using chain rule. Let's simplify the equation by cancelling out the density and then substitute compressibility of fluid C into the equation. Since C on the left side is small, we will have to neglect the whole term, and again on the right side it leads to total compressibility. Now we can rearrange the equation, and that's really a piece of cake. We've got diffusivity equation in terms of day and hours.
Next is the Bernoulli equation. The above discusses how a particle will behave along a streamline if there is unstable flow or steady flow. However, this needs to be applied or Bernoulli equation. In order to accomplish this you must realize that Bernoulli equation is obtained by integrating Newton's second law of motion, F equals to ma, or force equals to mass over acceleration. As a result, a general form of Bernoulli equation will become the following. So, P1 plus 1/2 of PV to PV squared 1 plus YZ1 equals to P2 plus 1/2 of PV squared 2 plus YZ2, where P is thermodynamic pressure and density is fluid density and V is fluid velocity, Y is specific weight, and Z is fluid height. So this is the example of Bernoulli equation. The formula is, for example, the Bernoulli's equation for left and right pipes. So each pipe has a pressure of 1 atm above it. So P left plus PGH left plus 1/2 PV squared left equals to P right at PGH right plus 1/2 PV squared right. So the density cancels out. So mahimo na lang siyang PGH left plus 1/2 PV squared left equals to PGH right plus 1/2 PV squared right. Put term with V right by itself. So it becomes to 1/2 V squared right equals to GH left minus GH right plus 1/2 V squared left. Multiply both sides by 2. So V squared right equals to GH left minus GH right plus 1/2 V squared left times 2. Square root by both sides. So V right equals to square root of 2 times 2 GH left minus GH right plus 1/2 V squared left. This distributive property. So V right equals to square root of 2 H left minus H right plus 1/2 of V squared left times 2. So substitute the answers. V right equals to square root of 2 times 9.8 m s over s squared times 0.03 meter minus 0.13 meter plus 1/2 times 2 meter over per second squared. So the answer is V right is equals to 1.43 meter per second. And that's all. Thank you.